We've spent some time looking at electrostatics, which is the fancy word for static electricity. All static electricity is when you force charge to build up in an area and you don't let it move anywhere. You might recall in a lot of our pictures I had a fixed charge. It wasn't allowed to move. Now we're going to ask ourselves, Kyle, what if you put those charges into wires and let them travel? What if you let them travel down a conductor? This is the basics of circuitry of all of the circuits that we have for all of our electronic devices. And I want to hopefully have you leave this unit with a vocabulary so that you'll understand a tiny bit, Lena, what your appliances mean when they tell me how many watts of power and how many volts and how many amps and things like that. So we're going to talk about Ohm's law, which you looked at in Science 9, but I'll teach it from scratch properly. Fill in the following key facts about voltage. How is voltage defined? And this you can get from the previous unit, the first time I mentioned voltage, if you look at your formula sheet. Yeah. Sorry? It's not newtons per coulomb. That's not voltage. Look at voltage, please. No, that where I defined it. Something over something. The amount of joules. Energy per coulomb. Higher voltage means each charge has more energy. Lower voltage means each charge has less energy. But you might recall I gave you an analogy, a gravitational analogy for voltage. I said I like to think of voltage as height. Higher voltage, to me, you've raised the charge to a higher height, and now they can roll downhill. And when they roll downhill, they'll give off some of that energy. What are the units? Well, since it's potential energy per coulomb, I guess it's going to be joules per coulomb. Give me 1 second here, please. Other words for voltage. Other words for voltage. Potential. So now we're going to start to talk about what's going on inside a direct voltage source. We're going to be talking about direct current. I'll mention a little bit about alternating current. Alternating current is what comes from the outlets. Direct current is what typically comes from a chemical battery. What's going on inside here? Inside here, there is some kind of a chemical reaction. And what's happening is charges are being separated from each other. You're doing work. Because in the same way as when you move between plates, let's say a negative charge from the positive end to the negative end, you're separating negative charges from positive charges, you're doing work. You're doing work inside the chemical battery. There's a chemical reaction that's going on to separate charges from each other. Charges are being separated, and so work is being done. And I'm using work in its physics context. There is some type of transfer of energy. Also, by the way, please don't think that inside a battery the electrons are at the bottom and the protons are at the top, because this is the positive end and this is the negative end. In real life, if you take one of these apart, you'll see that there's a tube running down the center, and the entire length of the tube is, I think it's positively charged, and there's a paste around it. I might be getting these backwards. That's negatively charged. Do a YouTube search for inside of a battery. You can take one of these, a battery apart, wear eye protection and wear skin protection. The acid isn't huge. There's typically battery acid in here. It's not hugely corrosive, but you wouldn't want to get it on your eyes or on your skin. the circuit symbol for a voltage source? It's a short line and a long line. The long line represents the positive end of the battery. The short line represents the negative end of the battery. So to help us understand what's going on inside electric circuits, I think it's helpful to have a mechanical analogy. And what I'm going to do, I stole this from other teachers that are better than me, I'm going to view every single circuit as a ski hill. Recall, I did say that the gravitational analogy of voltage was height per mass. So you can think of a voltage gain from a battery as behaving like the chairlift for a ski hill. A chairlift gives you more gravitational energy, height, mgh, and then going downhill, you lose that energy. A battery gives charges more potential energy, voltage, height, and then they lose that energy through a resistor. So a resistor is sort of like the ski hill. So potential or voltage is like height. Positive charges want to fall downhill in the same way that a ball wants to roll downhill. Potential energy due to gravity, mgh, is like the potential energy due to electricity, QV. The only reason the V doesn't have a constant in front of it like G is because how we define the volt. Current. Example 2. What happens if I connect a wire to one end of a voltage source, but not the other end? The answer is not much. I mean, like charges, and so there might be a couple of extra negatives that move down, but very quickly you've got enough negatives here that they're repelling each other this way, and you get an equilibrium point. Really, the short answer here is, what happens? Nothing. However, if the wire forms a continuous loop, now you're going to have electrons flowing. Electrons flowing, because like charges repel, unlike charges attract. They will be attracted to the positive charges on the other end of the loop. They will be repelled by the negative charges. But there is a problem with this circuit. You see, if this is a 6-volt battery, they will have to use up the 6 volts going through the wires. What did I say voltage was defined as? Okay, the problem with this is all of the energy goes into heating up the wire. This is a dangerous circuit because the energy's got to go somewhere. Law of conservation of energy says it's got to go somewhere. It would prefer to go into running some kind of a device, making a light bulb glow, turning on your iPod, whatever. Here, all that's going to happen is the charges are going to end up on this end. They will have lost their energy. They will have given it to the wire. The wire will glow red hot. So why is this a better circuit? Charges lose their voltage, which is their energy per coulomb, here, which means you're not going to heat up the wire anywhere near as much. In fact, diagram B has a special name. It's called the blank circuit. Anybody know? No? Okay, we'll put it in the notes later. It's called the blank circuit.
But like, it's not actually called a blank circuit.
No, it's called a fill in the blank circuit. Okay. This is called a It's a short circuit. Short circuit is when you have a voltage source connected directly to itself and there's no energy bleeder in between there. Then the energy is going to go into heating up the wires. Your stove elements are a controlled short circuit. They're designed to get hot, but it's a controlled short circuit. Nothing spectacular there. Electrons need a completed circuit for current to flow. Put your pencils down, look up. Here we go. Current. Current is defined as the rate of flow of charge. Current is defined as the rate of flow of charge. Anytime I talk about the rate, I'm dividing by time. Current is defined as Q over T. What would the units be then? Coulombs per second, and we give this a name. We call it an amp, named after Ampere, a scientist who did a lot of work with electricity. But an amp is defined as 1 coulomb per second. Higher amps mean more charges every second. This is why you're going to hear me say, if you're talking about electric shock, it's the current that does the damage, not the voltage. The voltage, what did I say voltage was like? Height. You can imagine a high voltage, low current being like 1 raindrop hitting you from 3 kilometers up. High voltage, 3 kilometers. 1 raindrop, you might not even feel it. Low current. As opposed to a swimming pool, lots of current dropping on you from the ceiling height, even though it's a low voltage, all that current, you're going to be feeling that. Current is what does the damage. By the way, also, Q is always the number of electrons times the elementary charge, or the number of protons times the elementary charge. So we can actually relate current to how many electrons are moving through a circuit. Example 3 says this: a 1.5 volt AA battery is rated at 0.750 amp hours. What's that? When connected to the motor in a portable CD player, the cell once upon a time, boys and girls, we used to listen to music on these shiny, silvery, wondrous discs called CDs. You put them into a slot, and a device would cause them to spin really, really fast. It was like magic, and you would listen to music that way. Now, I realize that that sounds like wizardry and fairy tales to you, boys and girls, but once upon a time, we used to listen to music on CDs. Lyndon, what's A asking me to find? It's asking me to find what equation have we just written down that has Q in it? How would I get current? How would I get Q by itself?
I times T.
So if I happen to know a current times a time, that will tell me how many coulombs of charge. Now, if you look up, I sort of have a current times a time, except my units aren't right. What do I measure time in? So if you get into electronics, in particular, if you get into RVing or boating, I have bought a boat, and batteries are typically rated in amp hours. They'll tell you, that tells you how many amps so I have a battery that has 100 amp hours. I can run 1 amp for 100 hours. I can run 4 amps for 25 hours. I can run 10 amps for 10 hours, roughly. They got to add to or multiply to 100. It's a handy unit. It's not an official SI unit, but it's a nice unit in electronics. So we'll have to do a mini conversion. We're going to go like this: 0.750 amp hours. From Physics 11, I want hours to cancel, so I think I'm going to put it on the bottom of the next fraction. I want seconds on top. Who remembers from Physics 11, how many seconds are there in 1 hour? 3,600 seconds in 1 hour.
60 seconds. That's how I do my time.
Oh, so it's going to be 0.75 times 3,600, which is what? I think 2,700? Now, you remember I said, so where's my AA battery? Here's a AA battery. I said 1 coulomb is enough to kill you. Technically, this has more than enough charge to be fatal. It's just there's no way you could get the charge out of here so fast for it to be fatal. It's a chemical reaction that's doing the work to separate the charges to make them available, and that chemical reaction is not very fast. You could safely put this in your mouth. I'm not going to because it's disgustingly dirty, but putting it in my mouth probably would complete the circuit, and I doubt I'd even feel it. How many of you have touched a 9-volt battery to your tongue, the rectangular ones? So you can try that. You'll feel a very weird tingle, so you're getting a tiny current going there, enough that it's interacting with your nervous system, which also runs on electricity. Caleb, what's B want me to find?
B wants you to find how many electrons are stored in the cell.
How many coulombs do I have stored in this cell?
2,700.
What's the charge on one electron?
1.6
0.6 times 10 to negative 11 coulombs. So how can I figure out how many electrons?
Just divide them.
The number of electrons is going to be the charge divided by the elementary charge. It's going to be 2,700 divided by, and since I just want a number, I'll ditch the negative. I don't want to say it's a negative number. I want a positive number of electrons. 1.6 times 10 to negative 19. How many electrons do I have available?
One.
1.6875 times 10 to 22. I'll go 1.69 times 10 to 22. And I guess the units would just be electrons. I don't know if I'll ever ask you B again. I might in the homework. I don't think I've ever put it on a test because that's not what's interesting to me. What's much more interesting is C. You'd like to know how long this sucker is going to last.
Yes.
What's this asking me to find? Yeah. Wait a minute, Mr. Dewick, isn't it 0.750 amp hours? Amp hours are not a measure of time. They are a measure of charge. Well, if I take this 0.750 amp hours and I divide it by how many amps are needed, can you see the amps cancel? And I'm left with time. What do you get? 3, I think. Bang on. Yeah. And that's where amp hours are handy. They let you, through some reasonably simple mathematics, make a pretty good guess as to how long your device will last. As an example, if you're an RVer and you know how many amps your refrigerator draws, you know how long you can run it off the battery before you better start your vehicle up and recharge the battery for a while. Yeah?
Is it okay to give our answer in hours? Or are we gonna?
Times by 3,600? 10,800? Or am I off?
Yes.
The answer to your question is, on a test, I would prefer my answer in seconds. The answer to your question is, in real life, you would give the answer to a customer in hours. Or if you're RVing or boating, you'll do them. How many hours? I want to know. I bought a Kickstarter power pack last year in September. It's about yay big. It's a lithium-ion battery. It's about 12 pounds. They claim there's 130 amp hours in there. It's pretty good. It's designed to go camping with, and you can run a lot of devices for a few days off of it, and you'll be okay. So we'll see. In our ski hill analogy, the flow of charges in a circuit is like the flow of skiers up and down a ski hill. Kilograms per second versus coulombs per second. Electrons flow at a constant speed in a circuit. They don't speed up or slow down. So we'll pretend that our skiers don't ski faster or slower. They use their skis to all ski at a constant speed because they all want to hang out with each other. Okay. It's a bit of a problem, though. One problem is that in a circuit, it's electrons that flow. Electrons flow from negative to positive, but I would much rather have charges flow from positive to negative. It's much easier mathematically to think that you are losing energy when you go through the circuit and gaining energy from the battery. That just makes way, way more sense. And so, Sarah, we're going to define current. We're going to say that electrons moving to the left is mathematically the same as protons moving to the right. And current is going to be defined as the direction positives would move if they could. We'll say that protons are moving. I know they're locked in the nucleus and technically not moving, but I'm telling you mathematically the electron moving in that direction is exactly the same mathematically as the proton moving in that direction, and I will convince you over the next few days why it is much nicer to think about that. So what we call current then is actually the downhill flow of positive charges. Some books call this conventional current. We're just going to call it current. The key is it's in the opposite direction of electron flow. So if I draw the direction of electron flow, I'm going to do electrons in red. Electrons flow from negative to positive. But Kieran, that's going to be confusing. The current, which I'm going to do in blue, that flows from positive to negative. In other words, Lena, this is going to allow us to say that the battery gives energy to the circuit and the resistors bleed energy from the circuit, which is so much easier to think about rather than having to reverse everything. Why is it like this? Because Benjamin Franklin named the charges wrong. Benjamin Franklin is the first one who said what was positive and what was negative, and he didn't know about electrons and protons. And in hindsight, he should have named protons, he should have made those negative, and he should have made electrons positive. The math would be way simpler. Think about all the trouble you had in Science 9 because electrons are where all the chemical reactions are occurring, and you had, oh, I'm losing electrons. Losing makes me more positive. Shouldn't losing make you more negative because you lost? Well, they botched the signs. It's a minus, which is plus.
I think Benjamin
Get through it all? Yep. Ooh, wow, maybe not. Gonna have to blaze here. So this brings us to Ohm's law and resistance. Every circuit offers some resistance, symbol R, to the flow of charge. The circuit symbol for a resistor is a series of short wavy lines, which you might recognize from Science 9. So that symbol there, that can be a light bulb, that can be an iPod, that can be a toaster, it can be a stove, whatever. It's a generic resistor. This resistance is due to electric friction, where electrons are colliding with the atoms in the material that they are passing through. The electrons lose some energy, and that friction is transformed into heat. The same way, similar to when you rub your hands together. A loss of energy also implies a loss of voltage because voltage is energy per coulomb. So, for example, if we had 8 volts right here, and if I had 3 volts right here, how many volts did I lose to heat traveling through the resistor? 5 volts. Lena's going to put her phone away for the remainder of class because she's just not that important. Face down. Thank you. The amount of flow, current, depends upon 2 things: the amount of resistance and the voltage applied. We're going to see if we can do a little thought experiment. What can you tell me about the current flow in each case? High resistance or low resistance? High resistance, think about a really narrow hallway. In fact, high resistance wires are narrow wires. If we had a really narrow hallway, could we get more skiers, more students, more current through it, or fewer students?
Fewer.
So as resistance goes up, current goes
Down.
okay. High resistance, and the symbol for current is capital I. Low resistance, which suggests to me in the equation that R will be on the bottom, because as R gets bigger, I get smaller. It's going to be a fraction, R is going to be on the bottom. What about voltage drop? I've told you that voltage drop is kind of like height. What's more popular on ski runs? Little bunny hill or good big hills?
Good big.
So higher voltage drop means higher current. Lower voltage drop means lower current. Since that matches small voltage, small current, big voltage, big current, the voltage variable is going to be on the top. In a word, it looks like this. Current equals voltage over resistance. The way you saw it in Science 9, we got the V by itself, and you saw it as V equals I times R. This is called Ohm's law. It's the one that's worth memorizing during this unit. You will memorize it because you get sick of looking it up. But I think you'll see it's one of only, I think I gave you 3 equations or 4. No, I think I gave you the resistor equations this year because I was nice.
Yeah.
So there's more equations this year. I take that back.
5.
Okay. V is voltage drop, measured in volts. I is the current running through the device, measured in amps. R is the resistance of the device. It's a scalar. The units for R we'll talk about. By the way, to be consistent with the previous unit, I really technically should write change in, except it just gets cumbersome. Ohm's law should really read delta V equals I times R, but the delta is dropped. So when you're talking about circuits, though, you really should think about, Caleb, going through a resistor as a voltage drop. The units of resistance are ohms, named after a scientist whose last name was Ohm. So Ohm's law, and Ohm also has a unit named after him. 1 ohm of resistance means that a voltage drop of 1 volt will give a current of 1 amp. 1 ohm is 1 volt divided by 1 amp. An ohm is a volt per amp, if you want to break it down even further. Okay. The symbol for ohms, why don't we use an O for ohms? What number does that look like? Yeah, I'm not going to go there. So use the Greek letter O, which is the omega. Looks like that. I always tell students, looks kind of like a mouse hole in a wall. Good conductors have low resistance. Poor conductors, insulators, have large resistance. I'm not going to test you on this, Sarah. This is just purely for a bit of nerd trivia. I've given you a bunch of resistances and a bunch of resistors. So these are scrambled up. Here are a bunch of different resistors. Read through these. Which of these do you think has the highest possible resistance, is the best insulator? We use it in industry all the time. Read through. Which one do you think has the highest resistance? No. We use it as an insulator all the time. Really? Yes, glass. Glass. What's the highest resistance on the right-hand side? Eric. Glass has approximately infinite resistance. I mean, okay, if you send a really massive current through glass, you can get through, but it's a pretty good insulator. Cheap to make, easy to make. Glass or ceramic. If you ever looked at power lines, the big metal ones, the black things that they run through when they get to the towers, that's some type of ceramic with a nearly infinite resistance to make sure that the power can't arc into the metal towers. Which of these do you think would have the lowest resistance? Copper wire has a resistance of about 0.1 ohms. Of the ones that are remaining, which do you think has the highest resistance?
The average resistance.
Nope.
Which light bulb?
Nope.
Huge.
It's skin. We're actually, on the outside, a pretty good insulator. Kevin and I completed that circuit earlier. Did you feel it at all, Kevin? No. The human skin has tens or hundreds of thousands of ohms, depending on how much moisture there is, whether there's moisture on your skin. There's other factors, but okay. Of the three remaining, which one do you think has the highest resistance? Now, here's a hint. High resistor often means high heat generation because you're losing a lot of voltage, which is energy per coulomb, in that resistor. And an easy way for that energy to go is heat. So of the three remaining, which one gets pretty hot? Light bulb.
Light bulb.
So it's got about a... And again, let me emphasize, I'm not going to ask you to memorize these. I'm just showing you with a bit of thought. We can puzzle this out ourselves. So we have 5 ohms and 200 ohms. And we have an average lab resistor or an electric motor coil of wire. Which of these do you want to run with as low temperature as possible?
The
Motor. Electric motor, typical electric motor. About 5 ohms. And I have a whole bunch of 200 ohm resistors in a lab. I'll show you them some other time. Kicking around. Now, I should be clear if we get technical here. We are going to treat our resistors as constant. In real life, as temperature goes up, resistance changes. It depends on other factors as well. So we're going to ignore these effects and assume that our resistors are constant. Human skin is a good insulator, typically tens or hundreds of thousands of ohms. It will only protect us to a certain point. When the voltage exceeds a certain value, the skin will break down. It will ionize the same way that air ionized to create lightning. Your skin will ionize and pass electrons from skin molecule to skin molecule to skin molecule. And on the inside, we're basically salty water, which is a really good conductor. So, once beyond our skin, the danger to our health lies in 2 effects. First, there is the heating up of tissue as electricity flows. This can cause severe burns and destroy internal tissues and organs. You need a really high current for that. Secondly, though, the flow of electricity through the body can disrupt the body's own electric nerve impulses, which can lead to temporary freezing or paralysis. When those muscles are the heart and the lungs and the diaphragm, that's a bad thing if you can't make those move. So once beyond the skin, the burning effect grows larger with larger currents. But the muscle paralysis, you don't need a big current, typically around 100 milliamps, which is 0.1 amps. In fact, it's nicknamed the death current. If across your heart there's 0.1 amps, that will be enough to cause your heart to fibrillate, to start to beat erratically or stop altogether. 100 milliamps is not very big. So, in our ski hill analogy, we've said the voltage source, the battery, acts like a chairlift. It gives the skiers more potential energy. We've said that the current is like the number of skiers. Higher current means more popular ski run. What is resistance like? The resistors themselves are like the ski runs, where you lose height going down a ski run. Going through a resistor, you're going to lose energy going through the resistor. And you know what? The resistance itself, let's say that's how deep the snow is. High resistance, the snow is so deep you can't get many skiers on there at once because you can't go very fast. Low resistance, perfect snow, lots of skiers. So Ohm's law for ski hills says that the flow of skiers varies directly with the height of the mountain. As voltage goes up, current goes up. Inversely with the depths of the snow. As resistance goes up, current goes down. High mountain, high speed, larger ski flow. Low mountain, low speed, lower ski flow. Skier flow, current, equals height over snow depth. Find the current in each case. Well, if I equals V over R, what's our voltage source in the left-hand circuit? Don't overcomplicate this. What's our voltage source in the left-hand circuit? I'll give you a hint. It's a number with a V next to it. 6. What's the resistance of this circuit in the motor? How many amps will flow through this circuit? 0.24? Now remember, amps is coulombs per second. This battery will last a fair while because not many coulombs per second are being drained from that chemical reaction. Now compare that with this short circuit where there's no external resistor, where we've only hooked up the wire, which means the wire itself has to behave like the resistor. Six. What's the resistance of this circuit? 0.001. How many amps are going to flow here? Probably if you leave this wire connected for very long, it's going to start to glow red hot, because to try and get 6,000 coulombs every second through that tiny wire means you're cramming way more electrons through there than 0.24 coulombs per second, and they're going to be rubbing into each other and generating more friction. And you're going to burn out the battery in about 5 minutes. You'll short the battery out very quickly because you're bleeding charge off like crazy. So this second diagram is an example of what's known as a short circuit. It's called short because it has a very small resistance, almost zero, and therefore a massive current. This depends, of course, on the voltage source. If you short circuit a AA cell using lab wires, you'll drain the cell battery really quickly, but you probably won't get the wires very hot. If you short circuit a car battery using lab wires, that car battery has enough charge stored to make the wires hot and possibly even melt them. If you short circuit BC Hydro with a lab wire, you'll create a dangerous situation in your house wiring that will cause a circuit breaker to interrupt or a fuse to blow. And I'll explain to you why that's the case in another lesson. Be careful with electricity. Electric meters. Current and voltage, and you will need to know how to read and place an electric meter for this unit. Current and voltage are measured using ammeters. I don't know why it's not amp meters, but the P is not pronounced, not even written. So you measure amps with an ammeter, and you measure volts with a voltmeter. You measure ohms with an ohm meter. Consider the following real circuit. So here is a 6-volt battery and a light bulb. Here is the equivalent circuit diagram. If I want to measure current, to properly measure current, I could not do this. Don't write this down. If I did that, some skiers could go this way and I would have no way of measuring them. Current is how many skiers. If I want to measure current, what I would have to do is physically cut the wire, let's say right there, and splice in an ammeter so that all of the current goes through the same location. Here is what I drew here. I would need to break the circuit, and then we say I would need to insert it in series if I wanted to measure the current properly. If I didn't insert it in series, I would get an inaccurate measure of current. This would be incorrect, because current would flow through here, and you would have no way of knowing how many amps went that way, because you're only counting. You can imagine an ammeter is like somebody standing at the entrance of a ski run, clicking on a little counter as each skier goes past. Well, if they were able to go down a different ski run, how would you know? Voltmeter is exactly the opposite. If I want to measure voltage, voltage really is the height, and the only way that you can measure the height of something is to measure how high it is at the top, how high it is at the bottom, and then subtract. That's the drop through that hill. If I want to measure the height of a ski hill, I need to figure out how high I am right here, I need to figure out how high I am right here, and then I subtract. And so voltmeters are set up in parallel. You cannot run a voltmeter like this. This would tell you the voltage at any one location, perhaps, but it doesn't tell you how many volts you've lost going through that ski run. It doesn't help you at all. So we don't break the circuit for a voltmeter. We connect it in, fancy word, parallel. More on those words later. Little technical comment. We focused our introduction on direct current. Direct current, DC, always flows in the same direction as a constant value. A lot of what I'll be teaching you also works to alternating current. Alternating current, AC, has a magnitude that varies as a sine function. Alternating current, it's an awful lot like that. It's a trig function. I can't assume that you've all done trig. Some of you have, some of you haven't, because I know not all of you are in pre-calculus 12. So it has a direction that's usually changing. The AC power that BC Hydro delivers to our homes has a frequency of 60 hertz, so it's changing 120 times per second, and a voltage amplitude of 110 volts. It's actually 113.4, but typically we round it off to 120 because the math is easier. So typically you'll hear an electrician say, yeah, 120 volts is coming out of that outlet. In household circuit calculations in this unit, I will use 120 volts for easy math. What's your homework? 1, 2. Three. Skip 4. 5. 6. 9, good review. Pause there.